Hello, everyone. In this video, we will start a new chapter, chapter 22. We will introduce developing efficient algorithms. I hope you have already started to read this chapter. You may have some questions already. I hope this video will help address your questions. Algorithm design is to develop mathematical process for solving a problem. Algorithm analysis is to predict the performance of an algorithm. The preceding two chapters introduced classic data structures, lists, stacks, queues, priority queues, sets, and maps, and applied them to solve problems. This chapter will use a variety of examples to introduce common algorithmic techniques, dynamic programming, divide and conquer, and backtracking for developing efficient algorithms. Before introducing developing efficient algorithms, we need to address the question on how to measure algorithm efficiency. Suppose two algorithms perform the same task, such as search, linear search versus binary search. Which one is better? One possible approach to answer this question is to implement these algorithms in Java and run the programs to get execution time. But there are two problems for this approach. First, there are many tasks running concurrently on a computer. The execution time of a particular program is dependent on the system load. The execution time is not reliable. Second, the execution time is dependent on specific input. Consider linear search and a binary search, for example. If an element to be searched happens to be the first in the list, linear search will find the element quicker than binary search. It is very difficult to compare algorithms by measuring their execution time. To overcome these problems, a theoretical approach was developed to analyze algorithms' running time independent of computers and a specific input. This approach approximates the effect of a change on the size of the input. In this way, you can see how fast an algorithm's execution time increases as the input size increases. So you can compare two algorithms by examining their growth rate. So this is the growth rate. The approach we're going to use is called the big O notation. So we now look at the big O notation. Consider linear search. The linear search algorithm compares the key with the elements in the array sequentially until the key is found or the array is exhausted. If the key is not in the array, it requires n comparisons for an array of size n. If the key is in the array, it requires n/2 comparisons on average. The algorithm's execution time is proportional to the size of the array. If you double the size of the array, you will expect the number of comparisons to double. The algorithm grows at a linear rate. The growth rate has an order of magnitude of n. Computer scientists use the big O notation to abbreviate for order of magnitude. Using this notation, the complexity of linear search algorithm is order of n. This is the notation, and pronunciation is order of n. Let's look at these terms on best, worst, and average cases. For the same input size, an algorithm's execution time may vary depending on the input. An input that results in the shortest execution time is called the best case input, and an input that results in the longest execution time is called the worst case input. Best case and worst case are not representative, but worst case analysis is very useful. You can show that the algorithm will never be slower than the worst case. An average case analysis attempts to determine the average amount of time among all possible input of the same size. Average case analysis is ideal, but difficult to perform because it is hard to determine the relative probabilities and distributions of various input instances for many problems. Worst case analysis is easier to obtain and is thus common. So the analysis is generally conducted for the worst case. Now for the big O notation, we can simplify the notation. The linear search algorithm requires n comparisons in the worst case, and over 2 comparisons in the average case. Using the big O notation, both cases require order of n time. The multiplicative constant half can be omitted. Algorithm analysis is focused on the growth rate. The multiplicative constants have no impact on the growth rate. So let's look at this table here. We have the size n for 100 and 200. And this is the function fn. For this n over 2 and 100 times n, look at this, the time is different. So for this, n is 200 and the function is 100 times n is 20,000. But you look at this, the ratio here for this f200 divided by f100, and this is all 2. So that's the growth rate. And here is for this function fn, if the input size is doubled, and now you see the time is also doubled, it's 2 times more. Regardless, so what you're using here is all this is linear time. So the multiplicative constant has no impact on the growth rate. And that's why, and we're going to say this, order of n is the same as order of n times a constant. So the constant can be ignored to simplify the notation. We can also ignore non-dominating terms. Consider the algorithm for finding the maximum number in an array of n elements. If n is 2, it takes one comparison to find the maximum number. If n is 3, it takes 2 comparisons. In general, it takes n minus 1 times of comparisons to find the maximum number in a list of n elements. Algorithm analysis is for large input size. If the input size is small, there's no significance to estimate the algorithm's efficiency. As n grows larger, the n part in the expression n minus 1 dominates the complexity. The big O notation allows you to ignore the non-dominating part and highlight the important part. So the complexity of this algorithm is order of n. Ignore the non-dominating part. We focus on the dominating part, and that is very good, and to reduce the complexity of the notation, and we get the essence of this complexity. It's order of n. These are the useful mathematical summations for analyze algorithm complexity. We'll give some examples to analyze the algorithm complexity in the next video. Thank you for watching this video.